Hello. Are you taking this course? Introduction to Electrodynamics. I'm going to give a chapter summary for Chapter 4 in Electrodynamics for a college-level physics course. I have the other chapter summaries in my playlist down below, and I have worked problems too. So this is just like the bare minimum, what you need to know, or at least what I think is the most important thing to know in Chapter 4. Okay, so I got my notes right here. Let's just get to it. So Chapter 4. Look, that's a mistake right there. I was like, I'll leave that up there because it's, chapter, and I didn't erase the number. So it's about electric fields and matter. In the previous chapters, chapter number 1, we looked at just math, what math things you're going to need to know. Chapter number 2, we looked at just describing electric field, electric potential, and electric charge density. And then in chapter 3, we looked at the electric dipole and then how to do boundary condition problems. So here we are, what happens when you apply an electric field to some matter. So the first thing, let's just recall, right? We can define a dipole moment P as r rho dv. So the position for each charge and integrate over the volume, and you get the dipole moment. I'm sorry. The other thing is that we have the electric potential due to a dipole, 1 over 4 pi epsilon naught. No. Yeah, it is. No, it's not. If you know the dipole, it's P dot r hat over r squared. Right. And then we have the electric field due to a dipole, 1 over 4 pi epsilon naught 3 P dot r hat minus P all over r cubed. There's another version of that too in spherical coordinates, but I like this one because you can do it in Python, and you can get the same thing from that. Okay, but that's what we saw in the last chapter. Those are the things that we had. The first thing this chapter starts off with, which isn't super important, it's medium important. Suppose I have a dipole. I'll do it like this. There's my dipole, right? It's an actual dipole, and I apply an electric field. Well, what's going to happen is that dipole is going to have a torque on it. It's going to rotate to be in the same direction, want to be in the same direction. So we can calculate the torque on a dipole as it's P cross E. Is that right? It's P cross E. Yep. And that's the torque on a dipole. Remember, that's the dipole moment, P. We can also calculate the electric force on a dipole. So notice that one of the important things about the dipole is the dipole has a 0 net charge, right? But it still can have a torque. It can still have a force exerted on it. So, the book calls this N for torque. I don't know why. And over here, it calls dV d tau. I don't like those, so I don't do it. So the force on a dipole, F, is going to be P dot del, the del operator, operated on E. So you're going to get a scalar here, right? So you're going to take the P component and then times the partial respect to x in Cartesian coordinates, and then operate that on, so you'll get a sum, right? 3 terms, a sum, and you'll operate them on that. So it is kind of complicated, but that's how you can calculate the force. This is important because this says that if you have some matter with dipoles in it, then the dipoles are going to produce electric fields, and then you have the electric fields that created them that are there too. So those are the torque and the force. Not super important, but it is in there. Now, what is very important is polarization. Okay, so let me draw a picture. Imagine that I have a material. And so this material consists of a bunch of atoms that are polarized for one reason or another, like this. So you could represent this by just drawing the dipole moment vectors for each one, and that's really nice, right? Because it's a lot easier to draw. So those are the P values. P. We can also describe the polarizability. My camera moved, and I don't like that. I kicked it. Okay. The polarizability of the material, capital P, and I draw my P's like that, and this is the dipole moment per unit volume. So this will have some function polarization. So polarization and that's the dipole moment. Okay. So this is a bulk property, and this is a property of the individual pieces, whether they're molecules or atoms or whatever. Okay. Now, if I have a material that's polarized, maybe it's just built that way. Okay, we'll talk about what happens if it's actually neutral and it's an induced polarization. But let's say it's just built that way. Well, notice up here in this example, I'm going to put these in pink. So here I have these charges. Let's see, this negative and this positive are right next to each other. And so they pretty much cancel. But these up here don't. So it's almost as though there is an excess charge up on the top. And on the bottom, there's unpaired negative charges. So I get a surface charge density because of this polarization. Let's call this the unit vector in hat, and in hat down that way. Then I can determine the charge density, sigma b. This is called bound charge density, and I'll tell you why. It's going to be the polarization p dot in hat. That's right, right? Yep. Now, you can imagine some other polarization where it did not have a charge density. Imagine that I had some weird situation like a cylinder and the polarization is like this, which would be weird, but it could happen. In this case, in hat is always perpendicular to the polarization, and there's no charge density on the surface because of that polarization. So it's possible. Okay. Now let's consider another situation. Imagine that I have another circle, but I have a weird polarization like this. It's hard to draw. So here are my atoms or molecules or whatever they are. So if I draw the polarization vector, it's going to be this way, right? These are the dipole moments, so the polarization has some radial function to it. I am going to get a surface charge density, but let's not worry about that. The important thing is here I have a divergence in my polarization, and so I'm going to get these unpaired charges in the middle. And in this case, the polarization is radially outward, so diverging, then I'm going to have a negative charge density. So we call this a bound charge density, sigma b, and it's negative the divergence of the polarization. These two are really important, right? Because they both tell us how we can have bound charges. Okay, now we need to talk about bound versus free charges. Let's go back and take this example right here. The charge on this object is 0. The net charge is 0. Now, it is possible that I could put some extra charges on here. Maybe it has a surface charge because I rubbed it with something. So I can actually have bound charges, which are charge differences due to polarization, and then I can have free charges, which are just extra charges that don't have a pair. They don't have a partner. Okay, they're singles. So I can write the charge density as the charge bound density plus free charge density. And that's important. Because when we start talking about matter, we want to treat those two things separately. Because what happens in this material, if it's not permanently dipoles, then that depends on the charges and the external factors. So that's where we want to break it up. And this gets us to our first big idea, the displacement field. So remember that we have Gauss's law in differential form looks like this. Del dot E is rho over epsilon naught. Well, I can write that as the divergence of epsilon naught E equals rho. Now I'm going to write that as rho free plus rho bound, right? Because we already said we can write the charges as free charges and bound charges. Now I'm going to write the bound charges as rho free minus the divergence of the polarization. Now I'm going to move that to the other side. So I have, I can write this as the divergence of epsilon naught E plus P equals rho free. Here's where we define the displacement field. We're going to call the displacement field, the electric displacement field D, as epsilon naught E plus the polarization. And with that, we get a different flavor of Gauss' law. It's still Gauss' law, but now it says that the divergence of D is rho free. This is the same thing as that. Okay, but now we've separated in terms of free charges and bound charges, which are in that displacement field. So what this allows us to do is to take something like this. Here's some dielectric material, and maybe it has free charges too. And these free charges can induce dipoles in there. But when we use this version for Gauss' law, we just say, okay, it doesn't really matter. I'll deal with the material later, right? Because I'm just finding the displacement field is only dependent on those free charges. So outside here, if I use Gauss' law, it's just going to look like a charged sphere with, I don't even care about the surfaces, right? The material inside, because the polarization out here is 0. So once I find the displacement field D, I can find the electric field. Inside of here, I'm going to find the displacement field, and then if I want to find the actual electric field, it depends on the polarization. That's what the displacement field for. It's still just Gauss' law. Okay, now finally we have one more thing that I don't like. And again, if you want problems on that, if you can't find a particular problem, comment down below. If you look at the playlist link down below, I have a bunch of problems I've solved for this course, but this is just a chapter summary. Finally, I got to write this down because I can't remember it. We have induced polarization, P, as, what was it? Epsilon naught chi E times E. So this says that the polarization of some material, this is linear. I mean, it can be other situations, but in the easiest case, it's going to be proportional to the electric field. As you apply that electric field, it induces dipoles in the material, and you can find the polarization. Now, there's another version of this. This is the susceptibility of the material. It depends on the material. I'm not even going to write it down because I'll forget it, because I'm going to spell it. And then we have epsilon as epsilon naught 1 plus the susceptibility, and we call this the permeativity. I get that confused with the permeability. But what you really want is epsilon over epsilon naught, and this is that dielectric constant that you saw in your first physics course. But again, it's just different ways to describe this is the main thing, right? Saying that the polarization depends on the electric field. And there you go. That's chapter 4. I'm going through chapter 6 for this course. I'll talk to you later.